All right, so I'll be going through the memory shortcuts and analogies for mole concept and stoichiometry. Okay, so this will help you understand the mole concept and understand the calculation questions better and how you can actually solve it easily. And there will be examples, as you can see, for every memory shortcut or every analogy. Okay, so you can see how you can actually apply it to the question. So let's start with stoichiometry calculation. So like mole questions, right? They ask you to calculate something. Usually I use the 4Cs. Okay, so note that this order of the 4Cs will not always be the same. That means the order might be jumbled up. Okay, so first you convert quantities to number of moles. Okay, so whatever quantities the question give you, like the mass, the concentration, you convert it into number of moles if you can. Okay, regardless of what the question is asking for. Then the second thing is to write the chemical equation. So there will be a reaction, right, between two things, usually, two substances. So you're going to write the chemical equation of that. And the reason why you want to write the chemical equation, so that you can compare the mole ratio, okay, between two substances. Okay, if you don't understand this right now, you'll understand once I get into the example. Okay, and then finally calculate the final amount, which is what the question is asking for. So the question asks, calculate the mass of sodium chloride, then you calculate the mass of sodium chloride. If the question asks, calculate the volume of hydrogen, then you calculate the volume of hydrogen. Right, so these are the 4 steps. In most cases, you'll follow this order. Okay, so let's look at this example here. Aqueous sodium chloride can be prepared by titrating aqueous sodium hydroxide with dilute hydrochloric acid. So in this titration, 50 cm³ of 0.50 mole per dm cube sodium hydroxide was used. Calculate the mass of sodium chloride formed. So we start with step 1, which is to convert quantities into number of moles. Okay, what are the quantities given in this question? First is 50 cm³ of sodium hydroxide. So this is the volume of sodium hydroxide. And then 0.5 mole per dm cube of sodium hydroxide. This is the concentration of sodium hydroxide. So we are given volume and concentration. Therefore, we can actually use one of the mole formulas, which is volume times concentration, to give me number of moles. Okay, so I can actually find number of moles of sodium hydroxide. Okay, so it'll be the volume. Why did I divide by 1000 here? Because I want to convert to dm cube. Okay, I convert it to dm cube. Okay, I want to convert to dm cube so that when I multiply by the concentration, it is also mole per dm cube. So I'll get the number of moles. So volume times concentration will give me number of moles of NaOH. Okay, 0.025 moles. So that's step 1. Okay, what is step 2? Step 2 is to write the chemical equation. So this whole question is talking about sodium chloride being prepared by titrating aqueous sodium hydroxide with dilute hydrochloric acid. Okay, so your reactants are sodium hydroxide and dilute hydrochloric acid. So you have sodium hydroxide and hydrochloric acid. This is actually your neutralization reaction. So your acid plus base, and you should know that acid plus base gives you salt and water. Okay, acid plus base will give you salt and water. So the salt in this case is sodium hydroxide. Okay, sodium hydroxide and water. And then you have to balance the equation. So luckily in this case, everything is 1, 1, 1, 1. So you don't have to balance it. But most of the times you will need to balance it. Okay. So once we're done with the balanced chemical equation, let's look at step 3. Compare mole ratio between two substances. So you might be thinking, how do I know what are the two substances that I need to compare the mole ratio of? The first substance is the substance where you know the exact number of moles of. Is there any substance here that we know the exact number of mole of? Yes, sodium hydroxide. Right, we just found that the number of moles of sodium hydroxide is 0.025 moles. Okay, so that's the first thing, first substance that I want to compare. Then what is the second substance that I want to compare it with? It's basically related to what the question is asking for. What is the question asking for? Mass of sodium chloride. Okay, so I want to compare it with sodium chloride. And how do I compare the mole ratio? I look at the balanced chemical equation. So we have NaOH here, and we have NaCl. Then we look at the number in front. If there's no number, it means 1 lah. So the mole ratio between NaOH and NaCl is 1:1. Okay, this is the ratio. This ratio is important because from there we can actually find the actual number of moles of NaCl, sodium chloride. So we know that the actual number of moles of NaOH, sodium hydroxide, is 0.025 moles. So if we compare 1 to 1, NaCl moles will also be 0.025. Okay, and this will be the number of moles of NaCl. So we have found this, and then we can move on to the final step, which is to calculate the final amount. So what the question is basically asking for. So mass of sodium chloride is what the question is asking for. We found the number of moles of sodium chloride. So from here, we can actually find the mass of sodium chloride. So if you're wondering how do we manipulate the mole formula, so originally the mole formula is number of moles equals to mass divided by the relative molecular mass, the MR of the substance. But now I want to find the mass. So how do I manipulate this equation? Usually, to make it simple for my students, right, I ask them to draw a triangle. Okay, so it doesn't have to look very nice. Just draw a simple triangle and then split it into 3 parts like this. Okay, then we're going to put number of moles here, mass on top, and then MR on the bottom. Right. Okay, so from this triangle, you can see that mole equals to mass over MR. Okay, then if you want to find mass, it will be mole times MR. Okay, so if they are beside each other, you multiply them together. If it's one above, one below, the above divide the below. Okay, so mass divided by MR. But if you want to find mass, it will be mole times MR. So what is the number of moles of sodium chloride? 0.025 times the MR of sodium chloride. Okay, so I'm going to look at the periodic table. Okay, sodium, the MR is basically the bigger number. So if we look at sodium, it's 23. Okay, 23. Then chlorine is 35.5. So I take 23 plus 35.5 over here, add them up, multiply by the number of moles, which is 0.025. Then I get the mass of sodium chloride. So I keep it to 3SF, okay, 3 significant figures. And this is how you solve stoichiometry questions. All right. So sometimes the question will give you the chemical equation, so you don't have to write it down. Okay, but if the question doesn't, in most cases, you do have to write the chemical equation. All right, so that's for stoichiometry calculation. Next, let's talk about limiting reagents. Okay, so I like to use this burger analogy. Imagine an ordinary burger, right? It consists of 1 patty and 2 buns. Okay, so you have 1 bun here. Two buns here. And then you have a patty in the middle. Okay, this is your patty. And then these other 2 buns. All right. So you have 2 buns on top, one on top, one below, and then a patty in the middle. So the equation I'm going to write for this is 1 patty plus 2 buns will give you 1 burger. Okay, just like a normal chemical equation, but we're using burgers and patties and buns. So my question to you guys watching is, if you have 10 patties and 30 buns, how many burgers can I make? Okay, I'll give you 5 seconds. 5, 4, 3, 2, 1. If you said 10, you're right. Okay, so to make 10 burgers, how many patties and how many buns will I use up? To make 10 burgers, I'll use up 10 patties. Okay, because to make 1 burger, I need 1 patty. So 10 burgers, 10 patties. And I'll need 20 buns. Okay, so I have actually used up all my patties. Okay, because I'm given 10 patties and 30 buns, and I use up 10 patties and 20 buns. So since all my patties are used up, the patty is the limiting reagent. Okay, the substance, the reactant that is completely used up will be the limiting reagent. So in this case, since all 10 patties are being used up, the patty is the limiting reagent. And let's look at the buns, right? I'm given 30 buns, but I only use 20. So I still have 10 buns remaining. 30 minus 20, 10. So the buns are in excess, meaning that there is still remaining, even though the reaction has ended. Okay? So in short, limiting reagent is the reactant that is used up completely. Okay, it's the reactant that is used up completely, such that the whole reaction comes to a stop. So now, instead of burgers, let's look at actual chemical example. So magnesium burns in hydrogen gas to form magnesium hydride. Okay, and this is the, okay, let me adjust this. This is the chemical formula, Mg plus H2 to give you MgH2. Okay, then remember to balance. Just nice for this one, there's no need to balance because it's already balanced. If 4.8 grams of Mg is mixed with 0.2 grams of H2, determine the limiting reagent. Okay, so again, they're asking you to determine the substance that has been used up completely. So first, we follow the same 4 C's in stoichiometry. Convert the quantities to number of moles. Okay, so I'm going to convert the quantities given, which is 4.8 grams of Mg with 0.2 grams of H2. Okay, these are the quantities given to me. So I can find the number of moles of Mg and H2. Okay, so number of moles of Mg will be the mass divided by the Mr. So the Mr of Mg will be 24. Okay, so 4.8 divided by 24 to give me 0.2, 0.2 moles. Then number of moles of H2 will be 0.2 grams divided by, so hydrogen is, Mr is 1, but I have 2 hydrogen atoms, right? It's H2. So it's 1 times 2, so 2. 0.2 divided by 2 to give me 0.1 mole. Okay, so now that I found the number of moles, okay, pro tip, right? Let me give you a tip. If you can find the number of moles of 2 reactants, right? So in this case, the 2 reactants, magnesium and hydrogen, if you are able to find the number of moles of both of these, most likely the question is testing you on limiting reagent. Okay, so maybe the question won't even say determine the limiting reagent, right? But you will know that this question is testing you on finding the limiting reagent. Okay. So if you can find this question is most likely testing you on limiting reagent. Okay, so next step will be to compare the mole ratio because there's already the chemical equation here. So moles of Mg to moles of H2. So for limiting reagent, right, we always compare the mole ratio of the reactants. So the reactants are the ones on the left side of the chemical equation. So magnesium and hydrogen. We compare these two. Okay, so ratio is 1 to 1. Okay, so 1 mole of Mg will react with 1 mole of hydrogen. And then what is given to us? What is given is 0.2 moles of Mg and 0.1 mole of hydrogen. So which one will be used up first? Of course, the hydrogen, right? Because 0.1 mole of hydrogen will react with 0.1 moles of Mg. Okay, and then hydrogen will be completely used up, whereas I have excess Mg remaining. In fact, excess by 0.1 moles. Okay, so since hydrogen is completely used up, the limiting reagent is hydrogen. Okay, so that is for limiting reagents, the burger analogy. Okay, then the next key concept is percentage purity. Right. So the actual formula for percentage purity of a substance will be the actual mass reacted divided by the total mass of the sample. Which means, right, you're given the total mass of a sample of a reactant. Okay, but not all the sample will react with the other substance. Only a certain percentage of it will react, and that will be the percentage purity. Okay, then times 100% to get a percentage. So think of this basketball analogy. Imagine you throw basketballs into the hoop, right? Each time you make a shot into the hoop, the ball takes part in a chemical reaction. Okay, then you need 100 balls to enter the hoop in order for the full reaction to take place. So let's say you get 100 shots and you only make 50. That means 50 out of 100 balls took part in the reaction. So the percentage purity will be actual mass reacted will be 50 divided by total mass, which is 100 times 100% to give you 50%. Okay, then of course in chemistry, we're going to use actual substances, chemical substances like carbon. Okay, so let's look at this real example here. 6 grams of carbon burns in air and produces 15 grams of carbon dioxide. Okay, determine the percentage purity of carbon. So remember I said to convert quantities into number of moles, right? Now you're given 6 grams of carbon and 15 grams of carbon dioxide. But here's the catch. You only can convert one of them to number of moles. The other one will not be accurate. Okay, which one will not be accurate? The one with carbon. Okay, the one with carbon will not be accurate. Because you want to find the percentage purity of carbon, which already tells you that only a certain mass of the carbon took part in the reaction, not all the 6 grams of carbon. So if I use this 6 grams of carbon to find number of moles, it's pointless, right? It's not the actual amount that reacted in the air. Okay. So what I'm going to do for percentage purity questions, right? Find the number of moles of the product. Okay, of the product. Because you want to find the percentage purity of the reactant, so you look at how much product is formed, and then from there you compare to the reactant, and you see how much reactant actually took part in the reaction. So let's find the number of moles of carbon dioxide. Again, they give us the mass. So we take mass, 15 grams, divided by the MR of carbon dioxide, okay, which is 12 plus 16 times 2. So carbon is 12, then oxygen is 16. And you get 0.3409 moles. Okay, so this is the number of moles of carbon dioxide produced. Okay, the product. Step 2, write the chemical equation. So this is carbon burning in air. When something burns in air, it reacts with oxygen. Okay, so carbon plus oxygen gives you CO2. This is the chemical equation. And now I compare the mole ratio between two things again. Now what do I compare? I compare carbon dioxide with carbon. Very simple. Okay, carbon dioxide with carbon. The mole ratio is 1:1. Okay, based on the chemical equation, right? Carbon and carbon dioxide, 1:1. So the actual number of moles of carbon that reacted is 0.3409 moles. Okay, this is the actual number of moles of carbon reacted. And now that I know the actual number of moles of carbon reacted, I can find the actual mass of carbon reacted. So again, if you look at the triangle here, okay, this triangle here, this triangle, okay, mole equals to mass over mr. So mass equals to mole times mr. Okay. So I'll take number of moles of carbon that reacted, the actual number, which is 0.3409, times the mr or ar of carbon to give me 4.09 grams. So this 4.09 grams is the actual mass of carbon that reacted with oxygen, okay, that burn in air. And from there, I can find the percentage purity, right? Actual mass reacted divided by total mass of sample. So actual mass reacted is 4.09 grams. And what's the total mass given to us? 6 grams. Okay, the total mass of the sample is 6 grams. So 4.09 divided by 6 times 100% to give me 68.2%. Okay, so that's the percentage purity of carbon. Then again, leave it to 3SF for your answer. Right. Okay. Then today, the final concept that I want to go through is percentage yield. I believe it's the final one, yeah. Percentage yield. So the formula for this is actual yield divided by theoretical yield times 100%. So it's similar to percentage purity, but there's of course a difference. So the difference is, I'll explain it using this cookies recipe analogy. Okay. Imagine you follow a cookie recipe from a cookbook, right? And then the recipe tells you that what you are expected to get after following the recipe, you should get 20 cookies. Okay, so I tried the recipe, but I only ended up with 15 cookies. Because I'm not experienced. I'm not experienced baker. So some of the dough was stuck to the pan. Okay. So I'm supposed to get 20, but I only got 15. So the percentage yield is actual yield, which is 15. Okay, the actual amount that I got divided by theoretical yield, how much I'm expected to get, 20 times 100%. So percentage yield of cookies is 75%. Okay. So you can see how this is different from percentage purity. Percentage purity is for the reactant, but percentage yield is for the product. Okay, so let's look at the example below. 15 grams of iron powder was added to excess copper 2 sulfate solution. A mass of 9.5 grams of copper was formed. So calculate the percentage yield of copper. Okay, now right, you want to find the number of moles of the reactant, okay, which is iron powder, because you want to find the percentage yield of the product. So you find the how much reactant actually reacted, how much reactant actually took part in the reaction, then you compare it with the product to see the actual yield of the product, how much product was actually formed. So let's find the number of moles of the reactant, which is iron. So again, we are given 15 grams, which is the mass. So 15 divided by the AR of iron, which is here, 56. So 15 divided by 56 will give me 0.2679 moles. Okay, that is the number of moles of iron that reacted. Okay, because it was added to excess copper 2 sulfate. So iron is the limiting reagent, which means all of the iron took part in the reaction. Okay, that's why limiting reagent is important. Then second step, you write the chemical equation. So iron plus copper 2 sulfate to give you iron 2 sulfate plus copper. Okay, this is actually your displacement reaction. Then of course it's balanced already. So I'm going to move on to the third step, which is to compare mole ratio. So again, I'm going to compare the reactant and the product. So iron and copper. Okay, mole ratio is 1:1. So the actual number of moles, sorry, the theoretical number of moles of copper is 0.2679 mole. Okay. So this, I'm imagining like all the iron actually reacted with copper 2 sulfate to form all the copper that was supposed to form. And all the copper that's supposed to form will be 0.2679 moles. This is the theoretical yield. Okay, theoretical moles of copper produced. Okay, then what is the theoretical yield of copper? So the theoretical mass will be 0.2679 times 64, which is the MR of copper. Okay, mass equals to mole times MR to give you 17.1 grams. So I'm expected to get 17.1 grams of copper, but I only got 9.5 grams. Yeah, I only got 9.5 grams. So percentage yield of copper will be actual yield 9.5 grams divided by theoretical yield 17.1 grams times 100%. Okay, equals to 55.6%. Okay, so that is how you find percentage yield. I actually do weekly free crash courses on my Telegram channel. So check out the description below and you can join the free Telegram channel with the free crash courses. Thank you guys. I'll see you in the next video.